You should have out paper, something to write with, and a calculator. All right. Number 1, at an amusement park, a 96 kilogram bumper car moving with the speed of 1.24 meters per second bounces elastically off of a 135 kilogram bumper car that is at rest initially. We want to find the final velocities of the two cars. All right. So, what is the mass of that first bumper car?
96 kilograms.
What is the velocity of it?
1.24.
What is the mass of the second bumper car?
135.
What is its initial velocity?
0.
What are we trying to find?
Final velocity.
For each of them, right?
Mm-hmm.
Okay. So in order to find the final velocity for each of them, we're going to want to refer to these two equations that you were given yesterday, okay? By the way, these 4 equations are really the only 4 equations we'll have to use today. That's why I have them up on the board, all right? So, do you want to find the velocity of the first one or the second one first? First one, okay. Do we have to rearrange anything here to solve for this?
No.
No, thank goodness, right? So we're going to have 96 minus 135 over 96 plus 135. And whenever we have that V naught on the outside, that V naught is referring to the velocity that is not 0, okay? So it's referring to this 1.24 meters per second. That's what we're going to use as our V naught here. So when you think you have the final velocity of that first bumper car, let me know.
Is it negative 2.21?
Negative what?
Negative 0.21.
Yeah, it's negative 0.21. What are the units?
Meters per second.
Meters per second. Okay, any questions about that one? No? Okay, well now I need to find the velocity of the second one. So that's going to be 2 times 96 over 96 plus 135. And once again, we're multiplying by the 1.24.
Wait, why are we doing that?
Because no matter what, we're always going to multiply by the one that is not 0.
1.03.
What are the units? Okay. What kind of collision occurred with these bumper cars? An elastic collision. Okay. So this is, we have 2 things that are conserved here. What are our 2 things that are conserved?
Momentum, kinetic energy.
Momentum and kinetic energy. Okay. So let's look at number 2. When a collision occurs, how are the initial and final momentums of the system related? It's a conceptual one. Every other question is conceptual because you guys asked for some more conceptual practice. So when a collision occurs, how are the initial and final momentums of the system related? You guys just told me that conservation of momentum. Yeah, they're the same, you guys. The initial momentum and the final momentum are the same. They're the same. As Paul Hewitt would say, same, same. They're same, okay? Yeah, they're the same. Same, same. You know, the idea is that you like write as I write.
Oh,
All right, can I erase number 1?
yeah.
Okay, so we're moving on to number 3 now. Number 3 says we have a 1.35 kilogram block of wood at rest on a smooth table. Then we have a bullet of 0.0105 kilograms moving horizontally at a speed of 715 meters per second. and it's going to embed itself into the block. We want to know the speed of the entire system after the collision. If we have a bullet and it's embedding itself in the wooden block and then they're moving together, what kind of collision is it? Completely inelastic. What is conserved during a completely inelastic collision? Just momentum, right? Is anything else conserved? No. Okay. So, mass 1, we can consider our block of wood. Yep, it's 1.35 kilograms. What's its speed at the beginning?
0.
0. Okay, what's the mass of our bullet?
0.0105.
What is the velocity of our bullet?
715 meters per second.
What are we asked to find?
Speed of the collision.
Okay, will they be going the same speed or different speed after collision? They're going to be going the same speed because they'll have combined together and they're going to be moving together, okay? Now, what did you just tell me is conserved in a completely inelastic collision? Momentum. So wouldn't it make sense for us to use conservation of momentum to solve this? Okay. So that means we have M1 V1 plus M2 V2 is equal to M1 plus M2 times V final. Why do we have these in parentheses?
Because it's the same.
Yeah, because they're together now. They're joined. So they're going to have the same final velocity. So we can bring that final velocity out. Now, is there anything up here equal to 0 that we can get rid of? The M1 V1. We can say bye to that. So we have M2 V2 is equal to M1 plus M2 times VF. And what are we trying to find?
VF.
So what do we do to get that VF completely alone?
Divide by M1 plus M2.
Yes, we're going to divide by the M1 plus M2. So we'll have M2 V2 divided by M1 plus M2, and that should give us our final velocity, which means 0.0105 times 715 divided by 1.35 plus 0.0105.
Okay, I'm at 5.9.63.
Yeah, I got 5.52.
Yeah. Okay, it's 5 point what?
5.2
What are the units?
meters per second.
Meters per second. Oh, I forgot to put the 2. 5.52 meters per second. Okay, do you guys have any questions about that one? No? Okay, then while you're finishing up writing that, how about you tell me what happens to kinetic energy that is lost in an inelastic collision? Yes, it's transformed into other forms of energy. What kind of forms of energy could it be transferred into? Okay. Sound, heat, all of those kinds of things, okay? It's going to transform into other forms of energy. Will the energy be completely lost? No, why not? Because of the law of conservation of energy, right? It's not created or destroyed. It just gets changed around and transferred and transformed into other forms. All right, am I good to erase?
Yes.
Okay, while I'm erasing, go ahead and look at number 5.
What was that? What was this answer number 4?
We just answered number 4 together, yes, ma'am. Okay. Number 5. We have a 1,200 kilogram car, all right? And it's moving at 2.5 meters per second, which means that our first mass is this 1,200 kilograms. And what's the velocity it's moving at? 2.5 meters per second. Okay. It says that it gets struck directly from behind by a 2,600 kilogram truck going 6.2 meters per second. So our second mass is going to be 2,600 kilograms. And how fast is it going? 6.2 meters per second. So it's bigger and faster, right? Now, it says the vehicles are going to stick together after the collision, and we want to know their speed immediately following this collision. If they're sticking together, what kind of collision is it? Completely inelastic. Okay. So does that mean they'll have the same or different final velocities? They'll have the same. Okay, so we get to use conservation of momentum. Momentum. Randy, put your mask on. You're done eating. All righty. Is anything equal to 0 this time?
No.
Nope. Okay, and what are we trying to find?
Final velocity.
Okay, we still only have to do one thing, though. What's the one thing we have to move?
Divided by M1 plus M2.
Yeah, we just have to divide by M1 plus M2. Is this starting to make more sense, you guys?
Yes.
Woo! Awesome. So we've got 1,200 times 2.5 plus 2,600 times 6.2 divided by 1,200 plus 2,600. I'm assuming that one of you up here who likes to race each other already has the answer.
5.03.
What are the units?
Meters per second.
5.03 meters per second. Perfect. Okay. So number 6 is what happens to kinetic energy. That's, wait.
Yeah, you skipped.
I skipped the, okay.
4.
So let's do 4. You guys should have told me.
I didn't know that.
You said, oh, that's number 4. That was.
Because I was reading it differently.
Oh, you read number 6 as number 4.
Yeah. You guys should have noticed that. Because you're supposed to read it as we go. But how is the initial kinetic energy related to final kinetic energy in an elastic collision? They're the same, right? Because kinetic energy is conserved. Yeah, awesome. That's good. Okay, did somebody say they got a different answer than 5.03?
Wait, so what's sorry, we're discussing.
To which one, Shay?
Number 4, we're discussing.
Or they're the same.
Number 5.
Because in elastic collisions, kinetic energy is conserved. So the initial has to be the same as the final. Yep, same. Now, is somebody saying they got something different to number 5? That's what I was asking.
That's what we were talking about. But I did it wrong.
Okay, I was just done wrong. All right. So now 4 and 6 have been answered, even though I flip-flopped them because I just saw them the wrong way. Shay, 6 was what happens to kinetic energy in an inelastic collision. And remember, we said it's transformed into other.
Okay, so that's.
Yeah, I flip-flopped them. All right, number 7. Okay, number 7 is going to take a little bit more effort than we've been using. Okay, it's going to take a little bit more brain power. So on number 7, we have an 82-kilogram football player, and they're running in the positive y direction with a speed of 3.1 meters per second. So mass 1 is going to be that first player of 82 kilograms. And they're going in the positive y direction. At what velocity?
3.1 meters per second.
Should that be positive or negative?
Positive.
Positive. Okay. And then we have a 96-kilogram player from the opposing team running in the negative x direction at a speed of 2.4 meters per second. So our mass is 96 kilograms. And what's our velocity?
92.4 meters per second.
Awesome.
Looking funny.
So it says, assuming that the players remain together, what is their speed immediately after the tackle? If they stay together, what kind of collision is it? Completely inelastic, okay? So we draw a little picture here. We've got a reference frame here. We have got player 1 going in the positive direction, player 2 going in the negative x direction. They're going to collide and go off together at some angle. Bam, I'm gonna go off, okay? So we need to find out what is this final speed. And in order to find that final speed, we're probably gonna need a theta. All right. So do you see how this is gonna take maybe one more step than usual? Okay, so how about we start by finding the initial momentum for each of these players? The initial momentum for each of the players?
All right.
Right? Okay, so how would we find the momentum of player 1?
Mass times velocity.
Yeah, so their mass is 82 kilograms, and their velocity is 3.1 meters per second. So what is their momentum? 254 point what?
2.
What are the units?
Kilogram meters per second.
Awesome. Okay. Then we have the momentum of player 2. How do we find that?
Mass times velocity.
And don't forget that the velocity is negative, so we should get a negative momentum.
Negative 230.4.
What are the units?
Kilogram meters per second.
Okay. Now player 1, it's player 1 on the x or y axis.
Y.
And player 2?
X.
Okay. And we need to find a theta, don't we?
Yes.
So think back to when we did vectors. Vector addition and all that stuff. When we had 2 vectors and we wanted to find an angle, what would we do? Tangent. Good. Okay, we have an x and a y. If you guys remember correctly, tangent of a theta, is it x over y or y over x? Y over x. Okay, so how would we get just theta? Inverse tangent of y over x. So in order to find our theta that our players go off at, we're going to have to do the inverse tangent of 254.2 divided by 230.4.
What did we positive or negative?
Did I ever have you guys plug in negatives when we were doing vectors?
No. So it would be 47. It'd be 47.8.
47.8 what?
Degrees.
Oh, you don't need a second.
Well, if you put the 1, that's fine, but I was looking mainly for degrees because you guys didn't say degrees. Okay. Now that we have theta, we are in luck. We can find the final velocity now, okay? So I'm going to put over here that theta equals 47.8 degrees. And then I'm just going to erase this so that we can see how we can now find our final velocity, okay? When we do conservation of momentum, sorry, yesterday it wasn't that m1 plus m2. Remember, you had to split it up into x and y, okay? So if we did it for x, we'll have m2 v2 equals m1 plus m2 times vf. Then what did we put here? Cosine of theta, right? Okay? And then if we were summing them in the y direction, we would have m1 v1 equals m1 plus m2 vf what? Sine of theta. So which one do you guys want to use, cosine or sine?
Cosine, of course.
Cosine, okay. Well, if we're using cosine, what do we do to get vf alone? Yeah, we're going to divide by m1 plus m2 cosine of theta on both sides. So we end up with m2 v2 divided by m1 plus m2 cosine of theta, which, can you guys plug that in? You're not ready? Okay, well then I'll just start writing stuff in up here while you guys do your thing over there.
Negative 1.9.
What are the units? Meters per second. And if we wanted to be more purposeful with our direction, instead of putting negative, what could we put?
Left.
North of west, yeah. Or if you just put northwest, okay? Northwest. Any questions about number 7? No. Okay. Number 8. What do we call a collision and what the colliding objects stick together? Completely inelastic. Completely inelastic. Okay. You guys want to go ahead and start looking at number 9 while I get the board ready?
Yeah.
Okay, number 9. We have a cart with a mass of 0.12 kilograms moving with a speed of 0.45 meters per second. So our mass 1 is 0.12 kilograms. Our velocity for the first one, 0.45 meters per second. And it's on a frictionless air track, thankfully. And it's going to collide with an identical cart that is stationary. What does stationary mean?
It's at rest.
Yeah, it's at rest. So if it's identical, what's its mass going to be? 0.12. And what's its initial velocity? 0 meters per second. Okay. And they stick together, which means it's what kind of collision?
Completely inelastic.
Completely inelastic. We want to know the final and initial kinetic energies of the system. So we want to know KE initial and KE final. So KE initial, our initial kinetic energy. How are we going to find it?
What do you use that 1/2 MV?
Yeah, 1/2 mv squared. Are we going to do it for the first mass, the second mass, or both of them together? We really are only concerned with the first mass. Why are we not concerned with the second mass? Its velocity is 0. So what would its kinetic energy be? 0. So initially, we only have kinetic energy with mass 1. So we do 1/2 times its mass of 0.12 kilograms times its velocity of 0.45 squared. So what is our initial kinetic energy?
It's going to be 0.012.
0. Point what?
1215.
So we just put 1, 2. What are the units?
No.
Joules. Do you guys all agree with that?
Yes.
Yeah? Okay. Now, what do we have to find before we can find our final kinetic energy? Our final velocity. Good. What are we going to do to find our final velocity? No, that's only if it's an elastic. This is completely inelastic. Conservation of momentum. Awesome. So, do we have an initial momentum with our second mass? No. So we can say M1 V1 is equal to M1 plus M2 times Vf. So how do we get that final velocity alone? Yep, we're going to divide by the M1 plus M2. Let me know when you think you've got a velocity. Perfect. You guys agree with? You agree?
Yes.
Yeah.
What are the units?
I agree.
I did not get that.
What'd you get?
What did you
I
get?
got that. I got that.
Let me just get it.
Because I got this.
Yeah, I messed up.
It's okay. It happens. I don't know if I'd say that. Okay. Now that we have this, can we solve for our final kinetic energy?
Yep.
Okay. So now we have to add the two together, right? So we'll have 1/2 times m1, which is 0.12, times our final velocity, which is 0.23 squared, plus 1/2 times our mass 2, which is 0.12, times our final velocity, which is 0.23 squared. Since they have the same mass and velocity, there is a way that you can simplify this, but you don't have to, okay? You don't have to. If you just type it in like that, it's okay. Anna, is everything all right?
Can you tell me why you did that? Like that whole thing? Oh, final or never mind. I got 0.028.
You got what?
0.028. Oh, JK, I totally messed up one thing up.
0.006.
I forgot to see
Yes, 0.0063. Something really important, you guys, is that since this is a completely inelastic collision, what happens to kinetic energy? It's not conserved, so it transforms into other things. So you should always end with less kinetic energy than you started with. Your final kinetic energy in a completely inelastic collision should always be less than it was when you started. Randy, really? Thank you. Okay. Do you guys have any questions about number 9?
No.
Okay, well, I've got a treat for you. Flip over to the back. There's more.
Alright. Oh, wow.
10. What condition is required for momentum to be conserved in a collision? Think of it like I'm asking you a trick question.
Elastic.
No, it doesn't, because it's momentum. Momentum always conserved.
Momentum is always conserved. The only condition is that a collision has taken place. Because momentum is conserved in every single collision, no matter what. It's conserved in elastic. It's conserved in inelastic. It's conserved in completely inelastic. So the only condition required for momentum to be conserved in a collision is that a collision took place. That's up to you, hon. All righty, 11. We've got a hammer and a rock. Sure. Okay, hammer and a rock. So far, how I've done all these problems is just that whatever mass comes up first, I make mass 1. And whatever mass comes up second, I make mass 2. Okay, so for elastic collisions like we're about to do, you can't always do that. And listen to why, okay? It's because of these equations over here, okay? In elastic collisions, you always need to make mass 2 the one that starts out at rest. If there is one that starts out at rest, it needs to be mass 2, okay? In an elastic collision, if one of the masses starts out at rest, it needs to be considered mass 2. In this case, the rock, yes.
What happens if there are like 3 things that's in collision?
You do not have to do that.
Okay.
Mm-hmm. All right. So that means, like you said, that rock 2 the rock will be mass 2. And the rock has a mass of 0.19 kilograms. And we put it there because it's at rest. So we can say 0 meters per second, okay? And it's getting hit by a geological hammer, which means we've got an archaeologist on our hands, all right? Ooh, I used to teach archaeology. Did you guys know that?
No.
All right. So our first mass would be the hammer. The hammer has a mass of 0.55 kilograms. And what is its initial speed?
4.5.
Awesome. What are we asked to find, you guys?
The final speed of the rock.
The final speed of the rock, which means we're looking for VF2. Okay. This is why it matters that we put the second one as 0, because this is the equation we're going to need to use. This V naught right here is always in reference to the object that has an initial velocity. You are never going to put in 0 for this V naught. Okay? You never put in 0. You always put in the object that has a motion. So if we're looking for VF2, we're going to have 2 times mass 1, which is 0.55, divided by mass 1 plus mass 2 multiplied by our initial velocity, which was 4.5. Hold on.
I got 6.6. What you said? 9. I got 6.69.
Awesome.
I got that too.
That rock is going to be going pretty fast, huh?
I know. Hope you don't get hit by that.
Hope we don't get hit by that.
You won't have a burn after that. That's not funny.
Alrighty. If 2 cars collide at an intersection and they don't stick together, can you conclude that the collision was elastic?
No,
It was inelastic, not completely inelastic. Yeah, it could be.
It was just regularly inelastic. Okay, listen to why. And it completely like elastic. If it's elastic, okay. Didn't we say it bumps up like a bumper car? Okay. Does the bumper car like have damage after that? No, because remember we said if it's elastic, there's no deformation, right? Okay, if you hit a car and then you guys bounce off each other, aren't you going to have some sort of dent or something?
Yes.
Okay, so there's still deformation. The kinetic energy was still lost. It wasn't conserved. So it could be still inelastic. It doesn't necessarily mean it was elastic.
Wait, it's regular and not completely.
The only way it's completely is if they stick together.
Yep. Oh, yeah. That's what I call it everything.
All right. Another thing on number 11, you guys, just in case you forget which one you should make M1 and M2 and you're doing a problem. One of the things we talked about yesterday, remember when we did the bumper cars and we talked about these 2 equations? Didn't I say this one, that VF2, the object that's getting bumped into, is always supposed to result in a positive number? Yeah? So if you had confused which one to put as which on number 11, and you had solved it like the rock was mass 1, you would have ended up with an odd number, okay? And when something gets hit, we're always going to say that it has some sort of positive velocity at the end that it's moved with, okay? We've got Brittany standing on a skateboard. Her and the skateboard together are 61 kilograms. Since this is completely inelastic, it doesn't really matter which one we make 1 or which one we make 2, okay? Because Brittany starts off at chilling on the skateboard. She's at rest when she starts. She's not moving anywhere, okay? Then Dave tosses a pumpkin at her. Why? I don't know why. Maybe it's the Halloween season, and he's just like, here's a pumpkin. Go have fun with it, okay?
Just the whole pumpkin?
Just the whole pumpkin. The whole pumpkin is 3.7 kilograms. And when he throws the pumpkin at her, what speed do her and the pumpkin start moving at?
6.6 meters.
Negative. Yeah, 0.16. That's supposed to be meters per second. I don't know where my little slash went. Okay. Ooh, excuse me. We want to know what was the speed of the pumpkin. So this is inelastic. So can we use either of these? No. So what do you think we should use?
The third one.
Yeah, we're going to use conservation of momentum. Because like we said yesterday, you can always, pretty much always use conservation of momentum for collisions. Yes, ma'am?
Why is that?
Because it says when she catches it, she and the skateboard begin to roll backward with a speed of 0.16 meters per second. So that means after the collision takes place, they start to move backwards at that velocity.
Oh.
Mm-hmm. Okay. So you guys said the third equation?
Mm-hmm.
Do we need to write out M1V1? No, why not?
0.
It's equal to 0, okay? So we'll have M2V2 equals M1 plus M2 times V final. What variable are we solving for? So what do we need to do? All right, that's all we got to do. Let me know what you get.
I got 2.80.
Ooh, look at you on top of things. What are the units?
Meters per second.
Meters per second. Now, are you sure that it's supposed to be positive?
I don't think so. It's
moving backwards with the pumpkin. So
Yeah, it's negative. You should have plugged in VF as negative 0.16,
yeah.
which